Let's talk about radioactive decay. So, what is radioactive decay? It is a process whereby unstable nuclei that occur in nature go through a decay chain in order to achieve a more stable state. So, now let's talk about the different radiation types. The first one is alpha, and here's a Greek letter for alpha. So, what happens in alpha decay? In alpha decay, the unstable nuclei emit alpha particles which are identical to helium nuclei. So, let's go down here. Here's alpha, and the nucleon number is 4. If you go to prior videos on isotopes, I talk about nucleon numbers. And a nucleon number is the same as a mass number, or the number of protons plus neutrons, in this case, 4. So, why 4? Well, let's take a look at this. Here's helium. It's got a mass number of 4. So the change in nucleon number will be -4. And the change in atomic number is -2. And why -2? Well, let's take a look at helium. Here's the atomic number of 2. And atomic number, what is that? It's the number of protons. So now let's look at the second radiation type, in this case, beta. And here's a Greek letter for beta. So what happens in beta decay? In beta decay, the unstable nuclei emit beta particles that are identical to electrons. So let's go down here. Here's beta, and the nucleon number is 0. And when you think about electrons, their mass number is 0, hence the 0 here. So change in nucleon number will be no change. Now the change in atomic number will be +1. Why +1? Well, in beta decay, a neutron converts to a proton. So in this case, +1. So now let's talk about the last radiation type, in this case, gamma decay. And here's a Greek letter. So in gamma decay, there's no emission of particles. So therefore, there's no equation. So therefore, the change in nucleon number, in this case, the nucleon number is 0. So change in nucleon number is going to be no change. And the change in atomic number is going to be no change. So this may not make any sense to you right now, but once we start doing some problems, it will make more sense on how to apply all of this information. Now I'm going to go over some problems on radioactive decay. So let's start off with alpha decay. And here's a chart that I included on alpha decay, and we've already discussed this. So let's start off with the first problem. Uranium-238 emits an alpha particle when it decays. So what new isotope is formed? So here you have uranium, and the symbol for uranium is U. Now, in prior videos, I've discussed this annotation, and it's in the video on isotopes. The top number is the nucleon number, which we've already discussed. It's the mass number, or the number of protons plus neutrons. In this case, it's 238. The bottom number is the atomic number, or the number of protons. In this case, 92. So if you look at the periodic table of elements and you look for element number 92, you will see right here that it's uranium. So that being said, let's go back. So what happens in alpha decay? Well, alpha particles are emitted, which are identical to helium nuclei, which I've already discussed. So if you look here, look what's here, helium. Now, if you look at the top number, it's the nucleon number of 4, and the bottom number is the atomic number of 2. So here's helium. Its atomic number of 2. So that being said, you have this annotation here, Then you add it to, how do you come up with this right here? Well, the change in nucleon number is -4, which we've already discussed. So this top number is the nucleon number, 238. Subtract off 4 and you get 234. And then the change in atomic number in this case is, okay, here's 92. You're going to subtract off 2. So that gives you 90. So how did I come up with this? Well, let's look at the periodic table of elements. And we're looking for element 90. In this case, it's thorium right here. So let's go back. And the symbol is TH. So what new isotope is formed? It's thorium-234. So let's look at the decay chain for this. This is a decay chain right here. Here's uranium-238, and here's the new isotope formed of thorium-234. So when this uranium-238 goes through this whole decay chain, it becomes the most stable isotope of lead-206 right here. See how it says stable? This is a whole decay chain, emitting alpha and beta particles alike, see? So that's that. So now let's go to the next problem. Radium-226 emits an alpha particle when it decays. So what new isotope is formed? Well, let's look at this. Here's a symbol for radium, Ra. The top number is a nucleon number, in this case 226, and the bottom number is the atomic number, which is 88. Now let's go to the periodic table of elements. If you go to element 88, it's radium. There you go. So that being said, we already discussed this part, how we get the helium. So I'm not going to go over that. We already discussed it in this problem. And now you're going to add, okay, so how do we come up with the change in nucleon number? Well, you take this 226 minus 4 to get 222. And the change in atomic number is this 88 minus 2, which gives you 86. But how do we come up with this part? Let's go to the periodic table of elements and look for element 86. So element 86 is radon, and there it is. So that's how you get this Rn. So what new isotope is formed? It's radon-222. That's how we got that. So you go back to this decay chain. Here's radium-226, and the new isotope formed is radon-222. And once again, once you go through this whole decay chain, the most stable isotope formed is lead-206. So that's alpha decay. Now, let's move on. Let's go to beta decay. Once again, I've included this little chart that we already went over, so I'm not going to discuss that here. So let's go over some problems on beta decay. Iodine 135 emits a beta particle when it decays. So what new isotope is formed? Well, once again, we're going to use the same annotation. Here's iodine, the letter I. The top number is the nucleon number of 135 that we grabbed from here. And we had to put the atomic number 53. And you get that from the periodic table of elements once again. So let's go to element 53, and that is iodine. So what happens in beta decay? So in beta decay, beta particles are emitted that are identical to electrons. So if you look at this formula, here's the electron. And we discussed this earlier, which has a mass number of 0, or the nucleon number at the top. And then down here, you have, this is how you write the annotation for electrons. So this is just a given already. And here's a 1 minus. So this is a given already. And this is the annotation for an electron. So that's how you do that part. So now you're going to add to this. How do you come up with this part? Well, the change in nucleon number is no change. So this 135 stays as a 135. And the change in atomic number is +1, which I already discussed earlier, and how I got that. So this 53 plus 1 gives you 54. So you go to periodic table of elements to find out what that element is. So let's go to element 54, which is xenon, right here, xenon. So that being said, you get Xe. So the new isotope formed is xenon 135. So now let's go to the next problem. Carbon-14 emits a beta particle when it decays. So what new isotope is formed? Well, here you have carbon. It's a capital C. The nucleon number is 14, and the atomic number is 6. And if you go to periodic table of elements, you'll find that carbon is here, atomic number 6. So now you know in beta decay, you emit beta particles that are identical to electrons. So here's the annotation for an electron, the mass number 0, and this 1 minus right here, the charge. So then you're going to add it to, so there's no change in the nucleon number, so 14 stays here. Change in atomic numbers +1, so 6 plus 1 is 7. So how do you find out what this letter is? Well, let's go to the periodic table of elements, and you find out that atomic number 7 is nitrogen, which is the letter N. So here's the N. So the new isotope formed is nitrogen 14. And to learn more about isotopes, I do have videos on isotopes, and you'll learn why this annotation is the way it is. I don't go into that into much detail here because I've already discussed that in prior videos, but that's the annotation. So that's beta decay. And guess what? Gamma decay I'm not going to go over because there's no emission of particles and there's no equations to go over. So that's that in a nutshell.